Thanks for the introduction. Am I audible at the back? Great. So this talk is about network side channels in the cloud and our system Pacer, which is designed to mitigate network side channel leaks for infrastructure as a service cloud tenants. So let me start by explaining how network side channel leaks work. At a high level, an adversary observes the traffic shape of a victim application, which includes the packet sizes and timing, and from that, it aims to infer the secrets of the application. So consider an application running inside a virtual machine in the cloud, sending requests to an external client. An adversary with physical access to a network element in the path of the application can directly observe the traffic shape of the application. Alternatively, an adversary can rent a cheap, unprivileged virtual machine, colocate itself with the application's virtual machine in the cloud, and then generate cross-traffic that would induce contention with the application's traffic at a shared network link, which could be the NIC of the physical server or even a top-of-the-rack switch. And based on the variations observed in its own traffic due to contention from the application traffic, an adversary can indirectly infer the shape of the application's traffic. The plot on the right here shows an actual attack where an adversary could identify the unique sizes of different files from a corpus as these were transmitted. And the adversary could observe this and infer this simply based on the sizes and timing of spikes observed in its own ping traffic latencies. And prior work has shown that one can learn a lot of sensitive information just from the observations of traffic shape. For example, one can identify the web page requested, which video is streamed, content of VoIP conversations, and even users' medical and financial secrets from a health or financial service hosted as a software as a service application in public clouds. So as you can see, network side channels can reveal a lot of sensitive information, and this should be of concern for cloud providers. And we present a system called Pacer to mitigate these kinds of leaks for cloud tenants. At its core, Pacer shapes an application's traffic to make the shape independent of secrets. And we present an abstraction of a cloaked tunnel to enforce secret independent traffic shapes by design for an application. To mitigate the leaks for infrastructure as a service cloud tenants, we provide the design and implementation of a paravirtualized cloaked tunnel instance. And one of the key challenges in building such a tunnel is to ensure that the tunnel itself is secured from other microarchitectural side channels on the platform. And for this, we develop a novel masking plus batching-based mechanism, which I'll be describing in the talk. In the paper, we also discuss other ideas related to traffic shaping strategy and exploiting public inputs to allow for shaping bursty traffic of an application efficiently while still protecting secrets. We also provide a gray box profiler that can automatically compute traffic shapes for an application while requiring minimal inputs from the application itself. You can also find detailed evaluation results and a formal proof of the security of our system in the paper. Here, I will describe in detail the cloaked tunnel abstraction and its design for enforcing traffic shaping. So, the key abstraction of cloaked tunnel is essentially what encapsulates and shapes the network traffic between any pair of communicating nodes and can be used to shape the traffic of any arbitrary guest VM. The key property that the tunnel provides is that the shape of the traffic inside the tunnel is secret independent, so that an adversary cannot learn anything, even from observations of the traffic inside the tunnel. To achieve this high-level property, the tunnel endpoint needs to satisfy two high-level requirements. First, it needs to make the payload traffic unobservable. And for this, it must ensure that all packet sizes are secret independent. For example, they all have the same fixed size. An application's packet generation rate may vary based on flow control, which may be itself dependent on secrets. So the tunnel must hide this flow control information by transmitting dummy packets if there is no payload from the application. Now, to hide the padding and payload packets, all the packets must be encrypted after the padding, and the padding information must be injected in the packet headers in such a way that it would be delivered at the other endpoint, and that the other endpoint would generate similar responses for all the packets. Because otherwise, an adversary could see the differences in the traffic in the other direction and distinguish between padding and payload. The second high-level requirement is that the tunnel must ensure that all packets are transmitted at secret independent times, so preferably on a schedule that is predictable and public. And there should be no deviations from this schedule in a way that could be correlated with the application secrets. To protect the traffic of an application running in a cloud virtual machine, where there may be a threat from an adversary co-located on the same physical server, we need one endpoint of the tunnel to be integrated with the virtual machine's hosting server, covering the shared NIC of the server. The other endpoint could be implemented somewhere on the client's premises, such as in a middle box or even on the client device. Here, we describe the design of the tunnel endpoint for the cloud application. The other endpoint can, of course, be implemented symmetrically. So conceptually, the tunnel endpoint can be implemented by adding a shaping layer right at the top of a traditional network stack in the guest kernel. The application receives requests from the network, and it generates response and shares it with the shaping layer. The shaping layer installs a transmit schedule based on the traffic shape computed for the application, and then at each time defined in the transmit schedule, it generates a fixed size packet using the payload bytes from the application's response and adding padding wherever necessary. And then this prepared packet will go through the lower layers of the network stack. It could be encrypted using a traditional IPsec layer, and then it would be transmitted into the tunnel. Now, unfortunately, the simple conceptual design is still vulnerable to timing leaks that could arise due to microarchitectural side channels on the platform. Note that the packet transmission time is chosen at the shaping layer right at the top of the network stack, and the packet still needs to traverse several layers before it reaches the NIC. And it's possible that the application interferes with the execution of the lower layers of the network stack and induce delays in the packet transmission times, which could particularly be correlated with the application secrets. And so this could lead to secret-dependent leaks into the tunnel. To prevent such leaks, we must performance isolate the network stack right from the shaping layer, but ensuring performance isolation within the guest is infeasible almost. We could try to move the entire stack into the hypervisor, but even this is impractical because it makes the hypervisor's design complex. It forces the guest and its tenants to use the network stack provided by the cloud provider, which causes vendor lock-in. And moreover, simply moving the network stack into the hypervisor is still not sufficient to prevent side channel leaks into the tunnel. So with Pacer, we take a paravirtualization approach. We implement a component in the guest kernel called gpace, which is a loadable kernel module implementing packet padding and small changes in the TCP and the NIC's Ethernet rival layer. We implement a second component in the Zen hypervisor called hypace, which implements dummy packet generation, encryption of packets, and pacing of them when transmitting to the NIC. Together, these two components address the true requirements of the tunnel and help in guaranteeing freedom from network side channel leaks while transmitting packets in the tunnel. So the payload packets are padded at the padding layer above TCP inside the guest kernel, which ensures end-to-end padding. Dummy packets are generated in the hypace layer when there is delay from the guest in generating payload packet. And importantly, these have valid TCP sequence numbers, which it gets from the TCP sequence information, which is shared from the guest TCP layer. Hypace then encrypts all the outgoing packets, and it places them into the next transmission queue for pace transmission. And before that, it encrypts all these packets, which ensures that the payload would remain completely unobservable. Now, to ensure that all packets are transmitted at secret independent times, hypace follows a schedule, which is pre-computed as part of the traffic shape computation. But in order to ensure that each packet is really transmitted at precise times, we need to now performance isolate the hypace component. Note that this is a much smaller component compared to what we had previously that requires performance isolation. So to achieve performance isolation, we profile the execution delays of hypace, and we identify its worst-case execution delay under varying background workloads empirically. And then we ensure that each packet is transmitted after waiting for this worst-case execution delay of the hypace, starting from the next scheduled transmit interval. Now, this masking is expensive, so we amortize the overheads of masking by increasing the length of the transmit interval and transmitting a fixed batch of packets at the end of each interval. Finally, hypace responds to congestion signals from the network, and this is done by using the congestion window information, which is again shared from the modified guest TCP layer. And essentially, it pauses transmission on the schedule when there's congestion on the network, and it resumes transmission when the congestion is resolved. Note that reacting to congestion control signals is only required to ensure network stability and performance, it does not have any security implications because congestion is a publicly observable event on the network. You can find more details about our design and implementation in the paper, and now I will briefly talk about our evaluation. So we evaluated the security and performance overheads of our solution. For security, we evaluated the accuracy and precision of a state-of-the-art CNN-based attack classifier on the shaped traffic. And we also built a formal model of HiPace to gain confidence in its design and implementation. For performance, we analyzed the bandwidth overheads incurred due to Pacer's padding of static corpuses for different services, and the trade-off between the bandwidth overheads and privacy guarantees that can be achieved after using public input-based workload partitioning for traffic shaping. We also measured the overheads on client latency and peak server throughput sustained by a medical website that serves static medical web pages. And we also evaluated the client's experience when streaming videos from a video service, which is set up as both a single-tier application as well as a two-tier application. So we observed that Pacer incurs moderate overheads on bandwidth, latency, and the throughput for both the types of applications. The absolute latency overheads are significant, but they are still in the order of hundreds of milliseconds, which could be further reduced by optimizing the transmit schedules that we compute for traffic shaping. Nonetheless, the impact on the end client's experience is actually minimal. For example, we observed that the video client experiences no jitter when streaming videos despite traffic shaping. The exact overheads depend on applications data, workloads, and the public inputs that are used for computing traffic shapes. What Pacer provides is a way for the developers to configure the trade-off between the overheads that it's willing to incur and the privacy guarantees that it wants for its application. So to summarize, Pacer is a traffic shaping-based solution to mitigate network-side channel leaks for infrastructure as a service cloud tenants. It provides a secure by design solution in that both its traffic shaping strategy as well as its enforcement of traffic shaping is secure. It is also efficient as it allows to exploit public inputs to reduce the overheads of traffic shaping for an application, and it reacts to congestion control signals, thus providing a practically usable solution. And finally, Pacer requires minimal changes in the guest application to leverage the traffic shaping solution, and a modest amount of changes in the cloud hypervisor and the guest OS to support the solution. We have open sourced all of our code, and you could check it out if you were interested. And with that, I'll be happy to take questions. Thank you.